we've reached. We're gonna have lots of these.
Yeah.
Okay, you set the roll there. Okay, welcome everybody to our October FPGA seminar, and this month we have Naif, one of my Ph.D. students, and we'll be talking about the infrastructure we've been working on called Galapagos, and it's kind of a focus of a lot of the work of my students. So,
Thanks, Paul, for the intro. So, yeah, I'm going to be presenting a large heterogeneous deployment stack. Within the stack, there's different layers, and within the different layers, a lot of my colleagues have, specialized, and so I may give a shout out to a few people that are even in this room. Okay, so just the same old introduction as we've seen in a lot of computer architecture talks. Sure, the end of Dennard scaling limits our clock speed, so we have to be a bit more clever, and computer architects have looked at heterogeneous systems for this. So this heterogeneity is all around us. At the top left, in the very grainy figure that you see there, is supposed to be a diagram of the Snapdragon 630 mobile platform. And within this very diagram here, it's not just your standard CPU, but there is a DSP unit, there's a GPU. So the whole point is there are specialized units to handle different parts of your application. On the right-hand side is your phone that has that very same processor. At the very bottom, along with the peach and blueberries, is a Fitbit, and that's supposed to have a lot of sensors as well. So we have this heterogeneity, and here most of this heterogeneity is on chip, but it's not just limited to systems on chip. Data centers are large, and if you want to send requests to it, then you would be using the HTTP protocol to be able to communicate to it. You might have devices communicating using the programming language MPI. In order to communicate to these devices, you might have to use that programming model on top of it as well. Now, the other thing that was especially brought up to my attention from people in high-frequency trading is, sure, they want to be able to communicate to these other devices, but they don't necessarily want to have all the handshaking that a lot of these protocols have. So for example, they might want to be able to communicate to other MPI devices, but they don't want to have the same MPI handshaking, so they said, could we do a thin version of this? Well, if that's the case, then we would want to have it modular in such a way where you could replace your MPI protocol with your own custom MPI protocol that's just good enough to actually fit with your pieces, but might have a different implementation underneath the hood. So how do we abstract, and how much do we abstract away? So I like to call this abstract art, because it is an art, really. So it's balancing. You're balancing usually two competitive objectives: ease of use versus performance. I just looked up abstract art, and apparently this is very grainy. This is supposed to be fire in the evening. Kind of hard to tell by that.
Of course.
Yeah.
I see it. Not abstract. It doesn't say what it is.
Oh yeah, exactly. Well, I think the red here and the blue around it the red's supposed to represent fire, and the blue around it's supposed to represent the evening. But yeah, I'm not an artist. So, okay. So the next decision that we'd have to make is: do we want one monolithic abstraction, or would we want a stack? So a monolithic abstraction is one single abstraction layer. So one of the advantages of this is that you have everything optimized for a given application. So for example, your communication protocol can be tailor-made for this specific application. Now, the other approach would be to have a stack where you have several layers of abstraction, with each layer providing an API for the layer above. Examples such as a network stack. So why might you want to do that is that you might want to be able to swap different layers of the stack given your application. And if you know that there are many different application domains that can still share a lot of this, then we would want to use this kind of approach. For example, if we decide that we want to change our physical network connection from optical fiber to something else, we don't have to re-implement TCP to do so. Now, this is going to go into the FPGA abstraction stack that we've made here. So on the left-hand side is what we define as our own hardware stack, and on the right-hand side we use an analogous software stack. So as you can see, a lot of it does match up. So the physical hardware is the same stack, but on top of that we have a hypervisor which abstracts away an individual node in hardware, and we have something similar in software as well. On top of a single abstraction of a node, we have our middleware and network layer, which connects a bunch of these nodes together. And in the software world, we can see this as an orchestration or a networking stack. And on top of which, we have a communication layer, which is heterogeneous, to be able to connect our hardware stack to software devices. So at the very bottom, I'm going to just quickly describe what the physical hardware is. So here refers to the physical devices that we have and how they're connected. So it could be an FPGA, a CPU, sensors. So an example is at the bottom right-hand corner is one such setup, this dinky setup that I had when I was giving a demo in FCCM. So here we have two boards with our 1 gigabit switch and a laptop, and all of this is connected in one network. Here is an example of two different data centers, but we have the same abstraction layers built on top. On the right-hand side is one data center in quotes. It's the same picture that I showed. It's a Nexus board, a pink board, a laptop, and a 1 gigabit switch. The approximate value of that is $2,000, with most of it being my laptop. And on the left-hand side is we have a bunch of these MP sock boards connected via 100 gigabit cables, and the approximate value of what we see on the screen here is $100,000. So two very different data centers, but the whole idea is the same abstraction stack fits on top of it. So I'm going to go into what the abstraction stack is shortly. So next is the hypervisor layer. So this describes the abstraction of an individual FPGA. So other terminology also refers to it as a shell. The whole point of this is to abstract away all the I/O device to create a standardized input. So after this, all of the devices look like a stream in and a stream out. So as you can see, on the left-hand side, there's an FPGA that now, because of the hypervisor, looks like a streaming object in, a streaming object out. Shortly, I'm going to go into how we've turned that for CPUs and other accelerators. So CPUs with the right abstraction can also look like a streaming in, streaming out. And once you've standardized these interfaces, you can connect all of these things together. Next, I'm going to talk about the middleware layer. So this refers to the orchestration of these multiple nodes, and this is probably the meat of this presentation here. So this layer refers to how we orchestrate clusters of resources, and where the clusters of resources includes FPGAs and CPUs. And the whole idea is that, as we referred to earlier, that interfacing with one of these objects can be quite painful. Now that we've abstracted away these individual nodes, the middleware can actually do it for many nodes. So orchestration includes automating the connections between these devices and to give the user a handle to the entire cluster. So that whole process looks like this figure that we see here. On the very left-hand side is in the yellow diagram of, we see a bunch of kernels connected together. So this is the vision the user has, whereas these kernels are connected and their implementation is agnostic to the device that we have in the data center. Then, on top of this library of kernels, the user also provides cluster description. So this cluster description would say, could you put kernels XY on node 1? Could you put kernels AB on node 2? And could you use TCP/IP as the off-chip communication? So what that does is it goes into our tool flow, and our tool flow looks at, okay, you've specified your off-chip communication to be TCP/IP, for example. I'm going to transform all the Galapagos streaming packets into TCP/IP packets that are leaving the chip such that all of these nodes can communicate. And again, the user doesn't have to worry about that. The user doesn't have to address something differently because it's on another board. They would just be using the same communication protocol as if it was on chip. So the way that I like to see it is, if any of you have worked with Xilinx IP Integrator, where you have to plop all your kernels together, it looks like one board. And here, even in the Galapagos flow, it looks like one board with an extra couple of hints that you would provide to go off-chip. So these the cluster description files, the kernels that you would add, the tool flow. Okay, cool. So how does that happen? Well, Galapagos makes a couple kernels to allow off-chip communication. So first, we have what we see here as the network bridge and the router. The network bridge is responsible to do the network address translation. So it takes Galapagos streaming packets, and it knows that, okay, you want to send to kernel 5. Kernel 5 is on board 3. Board 3's IP address is this. So I'm going to add the correct encapsulation, and now I can make sure that this packet gets to the right off-chip board. The router that we have here has a global view of the system. So it knows what kernels are on chip. So for example, if kernel 1 wants to send something to kernel 2, it never needs to go to the network bridge. So router would say, okay, I'm just going to reroute that to kernel 2 that's on chip. But if it's not kernel 1 or 2, it has to look up the address and actually do the network address translation and send it off chip. So the very right-hand side are those kernels that we were talking about. All of these kernels are addressed with kernel addresses, so it's our own addressing scheme, just a 16-bit addressing field, where the user would, within each packet, would provide the kernel destination that they want to send it to. So we've talked about this. Okay, cool. And these slides. So here is the overview of what we want to achieve here. So on the left-hand side is 3 different kernels, and this is more of the logical description. This is what the user envisions, independent of the mapping. So here we have kernel A, kernel B, kernel C. Kernel A's destination, kernel is 0, kernel B's destination is 1, kernel C's destination is 2. And they can all address each other, right? Whereas with the appropriate cluster description files, it gets transformed into what we see on the right-hand side, where kernel A and kernel B are on one FPGA, kernel C is on another FPGA. What's not shown in this diagram is the extra IP cores that are necessary to do the network address translation to make sure that kernel A and B can send stuff to kernel C and vice versa. But essentially, the user is mostly assuming the cluster that they see on the left-hand side, and with Galapagos, they can turn it into what is on the right-hand side. So just some back-of-the-envelope calculations that we have here. All our IP cores that Galapagos adds can run at line rate. We've tested this with a 156 megahertz clock. For off-chip communication, we've seen that when kernels are communicating off-chip via TCP/IP, they are running at about 7 gigabits per second, and that limitation is because of the TCP/IP core. And when we're using layer 2 Ethernet, it's running at about close to 9 gigabits per second, and that's just because of the packet header overhead. And what's not shown is when they're actually communicating on chip, it's 10 gigabits per second, because that's what the math turns out to be with our current clocking. We could, in theory, clock it faster. So, and in terms of latency, the middleware IP blocks adds on the order of tens of cycles of latency that we see here. Next, I want to talk about the communication layer. So this is specifically used to communicate to CPUs. So this is a CPU library called libgalapagos. And also, I'm going to allude to how this library can be used to transform other accelerators as Galapagos nodes. So libgalapagos is a software model of what we've seen before. So the figure on the right-hand side is the exact same figure that I've shown earlier with the network bridge, router, and kernels. The Galapagos software kernel object is in this picture is an HLS module. And ideally, we wouldn't want the user to re-implement their module if they want to target a software model. So what ends up happening is, through the magic of C++, we wrap these modules up with our kernel wrappers. And now this allows the user to have the same HLS module communicating to other CPU kernels using our libGalapagos framework. It can communicate to FPGA kernels using libGalapagos. So again, it's to allow the user to have the same code such that they can target the heterogeneous platform here. The way that we've implemented this is the router is thread safe. So in other words, all the kernels are running independently of one another. We've re-implemented the router to have thread safe FIFOs such that all these kernels are running in parallel. The router has a routing function that we provided as a virtual class. So I've implemented one such implementation of the routing, but let's say that you want to experiment with the Galapagos framework itself, the hardware IP cores, you can actually rewrite your routing function. So what this allows the user to do is not to just experiment with their actual application, but if they actually want to change Galapagos IP cores, they can experiment with that here as well. Just a small optimization here. If the kernels are within one device, the router actually knows that, and we can use shared memory. The other thing that we have here is we have what we call external drivers. So the external driver is another virtual class that we provide, and one such implementation of that external driver is the network bridge here. So an external driver is anything that's not a kernel on the FPGA, on the libGalapagos module here. So the network bridge is not a module, not a user-provided module, so it's an external driver, and we've implemented this in a way in which it's reading network packets and transforming that into Galapagos packets. So the reason I've designed it that way is such that it's extendable for other devices. So let's say in the future it's not a network packet, it's a network bridge. You can, as long as you have the same interfaces, you can rewrite the network bridge to be a PCIe bridge, for example. And now we can communicate to other kernels that are connected via PCIe. And then I'm going to allude to more uses of this in a bit. Okay, so just again, some more rough numbers here. We've seen cores communicating at close to the peak performance that we've seen is about, sorry, that's supposed to be megabytes per second. I wish it was gigabytes. 500 megabytes per second internally on one machine. But there is a small limitation in terms of the TCP IP core that we're using, which requires smaller packet sizes. So if we adhere to those same restrictions in software, we actually see a performance drop of 300 megabytes per second. And that's also because inherently the cost to talk to your network driver, you have to amortize it over a large packet, whereas on an FPGA you can stream that at line rate. So these are limitations that don't necessarily apply to the FPGA, but are problematic on CPU. When I've simulated 2 different kernels on 2 different network nodes within one host, so using Open vSwitch, with Open vSwitch you can actually create virtual network clusters. I've seen orders of tens of milliseconds of latency. We can optimize this further by replacing the network driver with DPDK, which actually bypasses the Linux network stack. So, but that's on the to-do list. And if one wanted to do that, they would just have to rewrite the network bridge, and everything else would stay consistent. So I've alluded to this earlier. How can we map this to GPUs, TPUs, and other accelerators? Okay, well, we can map libGalapagos as a bridge to an accelerator here. So it's a very similar figure to what we've seen before. Instead of kernels, we have different accelerators, and for each accelerator, we need to make an accelerator bridge. So it can run on pretty much anything that has a CPU. So an example being the TPU dev board, which has an onboard ARM. Over here, the network bridge is responsible for translating Galapagos packets into, network packets into Galapagos packets, as we've seen before. But what the extra step that we need is to transform Galapagos packets into the accelerator-specific protocol. So an example for this is currently we're in the works of implementing a TensorFlow bridge. So that takes Galapagos packets, turns it into input tensors, and once we do that, actually, not only can we hit the TPU board, we can actually also get GPUs as well. So that's something that's neat. But that's specifically for TensorFlow, specific accelerators, but with the same approach, you can take it for any accelerator. So if you have your own accelerator that has its own protocol, if you make the bridge for that to turn Galapagos packets into that accelerator-specific input, then it would fit within this paradigm. So now just a quick intro of an application that we're working on. So telepathy is a communication layer for multi-FPGA machine learning inference. Actually, it's maybe now multi-FPGA CPU, GPU, TPU machine learning inference. The development is in progress, and this is essentially a machine learning communication layer. So one of the IP cores that we were using was the Xilinx Darius machine learning core. So it was a machine learning core that Xilinx donated to us. This works for a single FPGA, and all our stuff does is it takes that and makes it multi-FPGA. So we use Galapagos for the RDMA between FPGAs and CPUs. So again, the whole idea is once we do this, it would abstract away the hardware and networking specifics from the user. So this is essentially what the first stage would look like. On the right-hand side, we have our FPGAs. So each FPGA has the CNN kernel. So in the example that I talked about was the Darius kernel, but in theory, it could be any machine learning kernel that works on one FPGA. You can implement it here. And we have off-chip memory that the kernel needs, and we have our custom RDMA controller that uses Galapagos to communicate. So step one, telepathy would figure out what all the instructions are, and it would configure the CNN kernels with those appropriate instructions. So in this case, the instructions are specific to the Darius machine learning kernel. Also, on top of that, it would provide DMA addresses. Because again, telepathy has a global view of the whole multi-FPGA cluster. It knows the address space of the entire cluster. It can actually provide addresses for the multiple FPGAs to communicate with. So now this is the actual data path here. As you can see, the data path never will go through the CPU. So it computes a frame here, and it then sends out the frame eventually through the RDMA controller and to the next FPGA. But the point is that telepathy, which is running on a CPU, does a setup initially, sets up the DMA addresses and the instructions, so that's your control path. But once you have the data going, the CPU is out of the picture. And that's just our specific implementation. If you wanted to run this on a CPU, you're more than welcome to, because Galapagos allows that. Why you'd want to do it, that's another question. So the user provides an implementation that's agnostic to the neural net description. So let's just go through the animation a bit. Okay. And then the user then would provide performance requirements. So resource constraints, performance requirements. So first, the neural net description is agnostic to what you want. Then along with the performance requirements and resource constraints and the physical hardware that's available to telepathy, it would then partition it, figure out that, okay, you want this performance, this is what I have available, I'm going to partition this and generate the instructions accordingly. So it then makes the instructions, and then it makes the DMA addresses, which then it configures onto the cluster that we have here. And that's finally returned to the user. Okay, so I'm going to dive a little deeper into telepathy. Okay, so this can be divided into both a front end and a back end. So you can think of the front end being even agnostic to the machine learning kernel itself. So in the example that I was talking about, the machine learning kernel was the Xilinx provided Darius kernel. Whatever kernel that you want to use, the front end would be, here's a large neural net, I want to be able to partition it, and then generate instructions. Now, the instructions that I generate are specific to the machine learning kernel that we happen to use. So this, what we can allude to here is that if you were to change your machine learning kernel from the Darius kernel to something else, you would just have to rewrite the backend. And or also, which is also neat, is if you have a compiler yourself that can take a neural net description and generate instructions for your individual core, you would just have to plop that in here. So essentially it takes the single node compiler, and with our compiler front end, it adds the DMA instructions. We can turn it into a multi-node engine here. So lastly, one of our customers is a group at MIT, CERN, and Fermilab here, where they have their Large Hadron Collider to detect particles. They want to use FPGAs, or at least as part of their solution space, because for them, latency is also a constraint here. So on that note, that ends my presentation here, and yeah, I'm ready to take any questions.
So, I have a question. In your kernels that you mentioned, you have stream in, stream out. How does Galapagos handle, let's say, multiple streams in?
Yeah, so for now, each stream is a separate address. So if you were to have a kernel with multiple stream ins, then each kernel would essentially be considered as a separate kernel, or each stream would be considered as a separate kernel. So that could be a little messy. So for now, we assume that each kernel has a single stream in and a single stream out.
Messy in what way? The specification of the whole platform? Or
I think messy in the way of synchronization. So we would have to like, if you want to do something like that, you would have to have the user's kernel itself handle the synchronization between the two streams coming in.
Like you mean synchronization? You mean like a handshake before?
Yeah.
Is there any handshake? From one kernel to
we don't have any handshaking with Galapagos at the moment, but what I'm trying to say is, I guess there is no assumption of synchronization between the two separate streams.
Right, just data flow.
Yeah, yeah. So that would be. In theory, it should be. It is supported, but we haven't used it yet because of just synchronization issues.
Right.
Yeah.
And you mentioned, the other question was about buffering. When you have multiple streams coming in, how do you avoid deadlocks? Or because I mean, communication patterns could be really nonlinear, could be really difficult to predict sometimes.
Yeah. So
is there anything about that?
So right now, that's up to the user to handle.
Right.
At this protocol level, we don't handle it, but there are protocols above this that people are implementing. So I guess this communication protocol is the bare bones, right? And on top of which you can implement other communication protocols. So a colleague of ours is implementing the PGAS protocol on top of this, so that would handle some of that synchronization and buffering as well.
We have two people to help carry.
Yes, Ibrahim.
So I think I got confused with like telepathy builds on top of Galapagos. So like,
Yeah, so it's like an application layer for it.
okay, so if I have like another application that I would a big application that I would like to partition on different FPGAs, do I have to write something like telepathy, or how automated would that flow be?
Yeah.
Like you described the Holy Grail at the beginning of the presentation.
Yeah.
How far is telepathy plus Galapagos for
So-
generic applications from that Holy Grail?
So no, that's a good question, because actually I do want to get to the Holy Grail that I mentioned at the beginning, but the way that I'm implementing it right now is I'm going with telepathy first, restricting my domain to inference, and ideally take that and hopefully make it general for any graph. So that would be the continuation of that. But for now, the Holy Grail that I've shown in the beginning is there's still a bit to do before we get there. At least the first step we want to do is by restricting the domain, and hopefully we can see how to make it general. Marco?
Suppose that I'm using maybe telepathy or just any Galapagos application. And well, let's say it's telepathy, and I put together a machine learning and a and I say the performance requirements, and it's all working, and I'm happy. And then the next day, my boss comes in and says, I want it to go faster.
Yeah.
What would it take to make it possible for me to just click, a dial or something, turn it up,
Yeah.
and telepathy will change itself and just go faster?
So, in terms of effort, it wouldn't be that much. In terms of compile time, it'd be a lot.
Okay.
So, because all this is done at compile time, and FPGA compilation is, we all know, not the fastest thing. So with telepathy, because we've separated the logical description and the physical description, it would ideally just not be the logical description, but on just like part of the physical description, some extra parameters saying this is what my constraints are now. And based off of that, it would generate a new mapping. But the logical cluster is still the same.
I guess what I was hinting at more was, what would it take to make it possible to do this at runtime? Like have a certain amount of runtime.
Yeah. So I think to do that, so another way that we have considered implementing telepathy is instead of at compile time would be more so to implement overlays. So if we can standardize some sort of infrastructure to say that, okay, we know that at most, this is at most how many machine learning kernels that can fit within one FPGA, and based off of the requirements, we can then partition instructions, then that could be done at runtime. But that's a bit of stuff that we have to look into. Yep.
So obviously this is done to speed up the abstraction of the actual hardware underneath and make less of a hard coding for a specific platform. But do you have any idea about overhead required to implement this in terms of, let's say, how much extra resources it's going to cost FPGA fabric in this case?
Yeah.
CPU is fixed, so that will be penalty on the cycles.
Yeah.
But, because I think you mentioned that you are able to run at 156.25 megahertz and probably higher. That means you are not overloading the FPGA.
Yeah. Yeah. So I guess so this may even come back to the initial like motivation, right? So it's sure. In terms of the modules that we add, the overhead for that is very small. So it's on the order of like hundreds of LUTs, on the order of tens of cycles of latency, and can all run at line rate. But then the next question is, if you wanted to go multi-FPGA, how much of this stuff do you need anyway, right? So it's like, you would need some sort of communication protocol between these things. You would need some sort of off-chip memory controller to communicate between these things. So now if you remember at the very beginning when I talked about a monolithic stack versus having a stack of different abstraction layers, we could, if you know that your application is always going to be like this, then you could maybe tailor make a communication protocol that fits your application stack, and maybe you could get a bit more savings out of it. But in terms of stuff that's Galapagos specific, I would argue that we add very little. So yeah, you would need a lot of it anyway, is what I'm saying. Yeah,
I don't know if someone asked this already, but you mentioned CPU as a stream.
Yeah.
Can you elaborate how does that work?
So,
what's a stream in a CPU?
Yeah, essentially we have a bridge that's gets interrupted every time a packet comes in from the network stream, and then it writes it in as a stream into one of the kernels. And the stream is implemented using a standard queue. So it would just queue packets into a stream that your kernel is waiting for.
So in the CPU to kernel direct?
Yeah.
FPGA direct, I guess both ways?
So yeah, so the network bridge is constantly being pulled for data coming in, data coming out. And whenever data comes in, it gets put into a CPU kernel. And whenever a CPU kernel puts data out, then the router would hopefully get that packet to the network bridge, which would stream it out. So it's constantly running. Yeah. So that network bridge implementation might not be the most optimum, hence because of the polling, but more so importantly because of the fact that we have to do this through the Linux kernel, right? So ideally, if we were to just replace that portion of it with a more optimized network bridge, then I can see this working a lot better.
Now I know that in principle, nothing prevents us from doing that, but if I were to, you mentioned one of your platforms is 100 gigabits per second.
Yeah.
Does that mean that the Galapagos, the TCP, and all the infrastructure works at that speed?
Not yet. So currently, definitely not CPUs. Currently, I'm working with so as of like 4 weeks ago, with at FPL, the ETH Zurich group released their 100 gigabit TCP IP core. So I'm at the moment trying to remake a new bridge for that. So if we can get that working, then yes, we will get 100 gigabit per second working. Another colleague within my group who's not here, Clark, he's made a 100 gigabit UDP core. So if I was to take Clark's core and make a bridge for that, then Galapagos would also have 100 gigabit UDP as well.
Do you have any slide about the internal Galapagos packet format? How does that work? That must be very simple, I assume.
Yeah, it's just an axis stream. I don't have a slide for that, but it's an axis stream with a few extra side channels. So the side channel being the dest and like an ID for your source.
Right, that's the 16-bit.
Yeah, and the source is also a 16-bit, which says who I am. Yeah. For the most part, so the source was an added-on that I added later, and that's essentially, usually for on-chip communication, I don't think a lot of things need to know the source, but when I want to go off-chip, I manage the TCP network sessions using the source, so that's why I kept the source. But yeah.